Okay, so welcome to our lesson on rhombi, the plural of rhombus, and squares. And what we're going to be looking at today in today's lesson is the properties and characteristics of rhombi and squares. In blue over here, we start off with their definitions. And so a rhombus is a quadrilateral with four congruent sides. Of course, having four congruent sides is going to mean that both pairs of opposite sides are going to be congruent, and so automatically with a rhombus it is also a parallelogram, as is noted down here. Rhombuses and squares are parallelograms, as of course are rectangles. By definition, a square is a quadrilateral with four right angles and four congruent sides, and so you'll notice of course that the four congruent sides corresponds to the definition of a rhombus. And if we jump back very quickly to the rectangles lesson, you'll see our definition of a rectangle is a quadrilateral with four right angles, and that allows us fairly easily and maybe fairly obviously to conclude that a square or a quadrilateral will be a square if it is both a rhombus and a rectangle, and that is in fact captured in theorem 620. If a quadrilateral is both a rectangle and a rhombus, then it will also be a square. And so we've got a couple of pairs of characteristics or properties of a rhombus related to its diagonals. The first is that the diagonals of a rhombus intersect each other at 90 degrees. They are perpendicular. And the second characteristic is that each of the diagonals bisect the vertex angles. In other words, angle 1 is equal to angle 2, angle 3 is equal to angle 4. In fact, 1, 2, 3, and 4 are all equal because a rhombus is, of course, a parallelogram, and so opposite angles are congruent, and then they are bisected, and so the four pieces are all equal. Similarly, 5, 6, 7, and 8 will also be equal to each other. Both of these theorems, the ones mentioned before, 6, 15, and 16, are biconditionals. And what this means is they work in reverse order as well. So if a parallelogram is a rhombus, the diagonals bisect a pair of opposite angles. If in a parallelogram a diagonal bisects a pair of opposite angles, the parallelogram is a rhombus. Okay. And then the theorem 619 is, of course, a way of proving that a parallelogram is, in fact, a rhombus. If you are given a parallelogram, of course, we have both pairs of opposite sides congruent. If you are then able to show, in fact, that AB and BC are congruent to each other, it results in four sides being equal, and that, of course, is the definition of a rhombus, and that's why this theorem works as it does. Okay, and if we scroll to the bottom here, what we have is a little summary, and we have a Venn diagram over here, and what's good about this visual is that it's very clear that within the family of parallelograms, we have parallelograms, rectangles, squares, and rhombi. Then a rhombi has additional characteristics, so it is a parallelogram but has additional characteristics. So all rhombi are parallelograms, but not all parallelograms are rhombi. Similarly for rectangles, all rectangles are parallelograms, but that is not necessarily true, the reverse. And then when you combine the characteristics of a rectangle and a rhombus, you get a square, which has all characteristics of parallelograms, rectangles, and rhombi. Okay, so we're going to move on now to the examples to see how it is that these things are going to play out in the problems. So first of all, we're asked to find the measure of y. The key word, of course, is that FGHJ is in fact a rhombus. We are given the measure of angle J to F to K. That angle over there is 6y plus 7. We are given the measure of angle KFG, K to F to G is over there, is 9y minus 5. And so according to the theorem before, we have 6y plus 7 is equal to 9y minus 5, and that is because the diagonal of a rhombus bisects the vertex angle. And so what we're going to do is go ahead here and solve. So we have 3y is equal to 12, divide both sides by 3, y is equal to 4. Okay, moving on to example 2, we have to find the measures of the numbered angles, again given that it is a rhombus. And so what I'm going to begin by doing is filling in the key information. Of course, the diagonals intersect each other at 90 degrees, and whenever we have one 90-degree angle with intersecting lines, we have 4. And so we have angle 1 equal to 90 degrees. Angle SPR is 55 degrees. Of course, the vertex angles are bisected, and so angle 2 will also be 55 degrees. If we then use the other characteristic of a rhombus, namely that all 4 of the sides are equal, I'm only going to mark 2 of them. Those are the only 2 I'm interested in. Of course, PQR, triangle PQR, is an isosceles triangle, and that should allow you to conclude that angle 3 is also 55 degrees. Or, of course, we could use the fact that the diagonal bisects both of the vertex angles and that the vertex angles are congruent to each other, because this is, of course, a parallelogram as well. And so we have angle 2 and 3 both equaling 55 degrees. 55 degrees would also be the value of angle SRP for the same reason. And now the last piece is to find the measure of angle 4, which is simply going to be 180 minus 90, our right angle, minus 55, which is going to give us 35 degrees for the measure of angle 4. Okay, and so we move on to example number 3. Small detail missing in the instructions. So find the values of x and y that will make ABCD a rhombus. I want to just add in the word PALM, the abbreviation for parallelogram, because if we simply equate these expressions, that won't actually be enough to guarantee a rhombus. But if we already know it's a parallelogram and we need it to be a rhombus, then what we need is for consecutive or adjacent sides to be congruent to each other. So we would need 2x plus y to be equal to 2y plus 3. And of course, the issue we're going to have here is that you can't solve a system of equations which has got 2 unknowns with only a single equation. And so what we're going to need to do is use the fact that if this were to be a rhombus, all 4 of the sides would be congruent, and we're going to need to make a second equation, either equating x plus 12 with 2x plus y, or alternatively x plus 12 with 2y plus 3. So I'm going to make it x plus 12 equal to 2y plus 3, and we're now going to go ahead and solve this algebraically. No TI inspire this time, not for this unit. And so to solve algebraically, in this particular case, I'm going to solve using the substitution method. And so first I'm going to start by isolating x. So x is equal to 2y minus 9. So I'm moving the 12 to the right hand side. 3 minus 12 is minus 9. I'm now going to take that value and substitute it into the other equation in the place of x. And so our equation 2 times x plus y is equal to 2y plus 3, and I'm going to substitute in 2y minus 9 in the place of x, because x is equal to 2y minus 9. And so I'm going to just clean this up now. So I'm going to get 4y, 2 times minus 9 is of course minus 18, plus y equals 2y plus 3. Move all the y's to the left hand side, so 4y plus 1 is 5, minus these 2 leaves us with 3y. On the right hand side we have 3 plus 18, which is going to be 21, and that allows us to solve for y equals 7. Our last step is to take the y equals 7 value, substitute it back into this expression here where we have x, so it's 2 times y minus 9, 2 sevens 14, 14 minus 9 leaves us with an x value of 5 and a y value of 7. Okay, and now to our final example, actually quite tricky, quite difficult, and so we need to pay careful attention. So the instruction is to classify the quadrilateral with the most accurate name. Okay, and so we're going to begin over here. We've got a piece of the diagonal. One of the diagonals is shown as being bisected, and we have a 90-degree angle. We don't know if it's a parallelogram yet, and so we cannot go jump directly to the conclusion that it's a rhombus just because the diagonal is cut at 90. We have to know that it's a parallelogram first. Okay, and so what you can see here, I'm just going to highlight these two triangles over here. We can prove congruency between those two triangles using HL, hypotenuse, leg. We have the reflexive side. That in turn is going to allow us to conclude that those two sides of the triangles are congruent by CP/CTC. We then have the diagonals of my quadrilateral bisecting, which makes it a parallelogram, and a parallelogram that has consecutive or adjacent sides congruent then becomes a rhombus. Okay, example B. In this particular case, we know that those two sides are congruent, and that means, of course, that those two angles are congruent using ITB. We know that we have some parallel lines, and so using alternate interior angles, we'll also know that this angle is congruent. If we were able to show that this was a parallelogram, we would then be able to show that we have a parallelogram with a vertex angle being bisected, and that would, of course, show that it's a rhombus. And so hopefully you realize that if this angle is 50 degrees and this is 65, we can find our third angle over here by saying 180 less 50 less 65, and that of course gives us 65 degrees over here, which confirms for us that we've got a 65-degree angle over here by alternate interior angles. This angle over here is 65. Using ITB, this angle over here is 65, and so we have now got both pairs of opposite sides parallel, of course, because that 65 over here is equal to this one, so we have alternate interior angles. This guarantees that it's a parallelogram. It's a parallelogram with a diagonal bisecting a vertex angle, and this, of course, makes it a rhombus once again. Okay, so in the interest of time, I'm just going to knock off D, because that's a relatively straightforward one. The two 90-degree angles guarantee us that those are parallel. In turn, these two 90 degrees guarantee that those are parallel, both by consecutive interior angles being supplementary. And of course, if we have got consecutive interior angles between parallel lines, that of course means we've got a fourth 90-degree angle, not that we need it, but we now have a parallelogram with a 90-degree angle, which of course makes this a rectangle. Okay, a minute and a half before I run out of time, so I just want to wrap this one up very quickly. Again, we've got diagonals cutting at 90 degrees, but we cannot be sure that it's a rhombus or indeed a square unless we can prove that it's a parallelogram first. So what I'm going to use here is the fact that those two angles are congruent to each other, which gives us alternate interior angles. Okay, and so our alternate interior angles result in those sides being parallel, which guarantees, first of all, that for sure we have got a parallelogram, one pair of opposite sides both parallel and congruent. We then have a parallelogram with diagonals that are intersecting each other at 90 degrees, and so that is in fact going to raise the status from a parallelogram to a rhombus. And then the last piece, since this is a parallelogram, of course the diagonals will bisect each other, and if you then recognize the last piece of information, that these two angles are congruent to each other, then according to ITB, that means these two sides are congruent. Similarly, if these two angles are congruent, these two sides are, and we actually end up with the diagonals being congruent to each other and being cut at 90. That means it's also a rectangle, and that allows us to conclude that it is in fact a square.